Good morning, everyone. And my name is Bing Hui. And today I'll present my work, Stealing Hyperparameters in Machine Learning. And this is a joint work with Neil Gong, my supervisor. And machine learning as a service is an emerging technology to help users with limited computing power or limited machine learning expertise to learn machine learning models. And several machine learning internet giants deploy machine learning as a service platforms, like Amazon deploys Amazon Web Service, Google deploys Google Cloud Platform, and Microsoft deploys Microsoft Azure. And so how machine learning as a service is used by users. And this is an example. First, a user uploads a training data set to machine learning as a service platform, and then machine learning as a service train a machine learning model, and offers the users the prediction API. And then the user uploads a testing data set to query this prediction API to evaluate the performance. However, privacy is a big challenge for machine learning as a service. And for instance, the model inversion attack leverages the model predictions to invert the aggregate information of the training samples. And furthermore, the membership inference attack will train an attack model and to predict if an input is a training data set or not. And a model extraction attack will steal the model parameters by querying a learned machine learning model. And our work is a new privacy attack, and it is called the hyperparameter stealing attack. And hyperparameters are confidential for several machine learning as a service. And so our attack is to steal the hyperparameters used by machine learning as a service. And one application scenario is that a user is an attacker, and the attacker can learn a machine learning model using the machine learning as a service with much less computational cost without sacrificing the performance. So now I'll present our work using this outline. First, I will introduce some machine learning background, and then I will detail our hyperparameter stealing attack, and then I will evaluate our attacks and propose the defense. And finally, I will draw some conclusions. The machine learning background, the machine learning concepts. And one key concept of machine learning is the objective function. In this work, we focus on the supervised machine learning. The objective function of supervised machine learning consists of a loss function and a regularization. The loss function, for instance, can be a least square, and regularization can be L2 norm. And the loss function is related to the training instance and the label and the model parameters. And each instance is a feature factor, and the label can be a continuous value for regression problems and categorical value for classification. And the lambda is the hyperparameter. In this work, we focus on the hyperparameter that balance between the loss function and the regularization. However, and moreover, it can be generalized to multiple number of hyperparameters. Machine learning tasks. And given the objective function, machine learning has two tasks. One task is the hyperparameter learning. Usually, we'll use the cross-validation to learn hyperparameters. However, cross-validation is time-consuming. And the other task is model parameter learning. Model parameter learning is to learn model parameters by minimizing the objective function of a machine learning algorithm with a given hyperparameter. And different machine learning algorithms will use different loss function and regularizations. So given this, given machine learning objective and machine learning task, we can have this system. So first, given the training data set, we first use some hyperparameter learning algorithm to learn the hyperparameters. And then given the training data set and the learned hyperparameters, we will use some model parameter learning algorithm to learn the model parameters. And then we can use the learned model parameters and the hyperparameters to evaluate the new data sets. So now I will show our hyperparameter stealing attack. The motivation. Existing privacy attacks on machine learning systems focus on either inferring the training data set or stealing the model parameters. But the hyperparameters are also critical for machine learning algorithms. And learning hyperparameters is time-consuming. So motivated by machine learning as a service, an attacker could be the user who aims to steal the hyperparameter for saving economical costs. And the threat model, from two aspects. First is the attacker's goal. Attacker's goal is to steal the hyperparameters. And for attacker's knowledge, first, we assume that the attacker knows the training data set, and this is easy to satisfy because the user is always the attacker. And the second is that attacker knows the machine learning algorithm. We know that certain machine learning platforms will publish the machine learning algorithms. For instance, the Amazon machine learning will use logistic regression, and Microsoft Azure can use logistic regression or support vector machine. And third one is that we assume the attacker optionally knows the model parameters. If the model parameters are unknown to an attacker, then we can first use the model extraction attack to steal the model parameters. Now, a short attack framework. The key observation is that the learned model parameters of a machine learning algorithms are often a minimum or near a minimum of the objective function. And then the gradient of the objective function at the learned model parameters should be 0 or about 0. And in this way, we can encode the relationships between the model parameters and hyperparameters. And so we leverage this observation to steal the hyperparameters. It consists of two steps. In step 1, we set the gradient of the objective function at the model parameter to be 0. And then we have this equation. Here, for different machine learning algorithms, A and B are different. And this equation is a system of linear equations about the hyperparameters. And here, the number of equations is more than the number of hyperparameters. So this system is overdetermined. And then in step 2, we use least square method to estimate the hyperparameters as follows. And our attack is applicable to various machine learning algorithms. For instance, it can be applied to regression algorithms like ridge regression, lasso, and elastinate, and kernel ridge regression. And also it can be applied to classification algorithms like logistic regression, support vector machine. And moreover, it can be applied to neural networks. Here, we simply take attacking ridge regression as an instance. For more details about attacking other machine learning algorithms, you can read our paper. The objective function of ridge regression has a least square loss and L2 regularization. First, we set the derivative of the objective function with respect to the model parameters. And then we have the form of A and B. And then we have the estimated hyperparameter. Now the evaluation. First, I present our theoretical evaluation using two theorems. The theorem 1 is an exact estimation. That is, if the learned model parameters are an exact minimum of the objective function, then the estimated value, hyperparameter value, equals the true hyperparameter value. The theorem 2 is about approximate estimation. That is, if the model parameters is closer to the minimum model parameters, then the estimation error is bounded by this equation. Here, delta W is the difference between the learned model parameters and the true model parameters. And the estimation error delta lambda is a linear function about this difference. Now I do some empirical evaluation. I will use various data sets for regression and classification, and we evaluate many regression algorithms and classification algorithms. And we use the relative estimation error as the evaluation metric. The first result is assume that attacker knows model parameters. And then we have the results for different algorithms. First, with x-axis here is a range of true hyperparameters, and the y-axis is the relative estimation error, both in log10 scale. And here we see that the y-axis value of all figures are below -2, which indicates that the relative error is about 1%, which is very small. And for ridge regression and kernel ridge regression, we have an exact estimation because we have the analytical solutions for regression and current regression. So we have these two observations. First, our attack can accurately estimate the hyperparameters for all our studied machine learning algorithms. And our attacks can more accurately estimate the hyperparameters for machine learning algorithms that have analytical solutions of model parameters. And this result is to show that if the model parameters are unknown to an attacker, similarly, the x-axis is a range of hyperparameters, and the y-axis is the relative estimation error. And here we see that the y-axis value are all below -5, which indicates that our attack can also applicable to these algorithms, even if we do not know the model parameters. So these results show that our attack can also accurately estimate these hyperparameters when model parameters are unknown. This is because we first used model extraction attack to steal model parameters, and the model extraction attack can accurately steal the model parameters. Now we evaluate our attack on a real machine learning as a service, the Amazon machine learning. Here we use two methods that users will use a machine learning as a service. The method one, this method, the user first will upload an entire training data set to Amazon machine learning, and Amazon machine learning will use the entire training data set to learn hyperparameters and the model parameters, and then they will the user will evaluate the testing data set by querying the learned machine learning model. However, this method is accurate but inefficient. This is because M1 used the entire training data set to learn model parameters, so it is accurate. However, it also used the entire training data set to learn hyperparameters, so it is efficient. So another choice is M2. In M2, a user will upload a subset of the training data set to Amazon machine learning, and then the Amazon machine learning will learn hyperparameters and the model parameters over this subset, and then the user will evaluate the testing data set by querying the machine learning model over this subset. This method is efficient but inaccurate. This is because M2 used a subset to learn hyperparameters, so this is efficient. However, it only leverages a subset of the data set to learn model parameters, so it is inaccurate. So to address the issue of M1 and M2, and we propose a technique, we propose method 3, which use a train, retrain, and train, steer, and retrain strategy. The detail is as follows. First, the user will upload a subset of the training data set to Amazon machine learning, and Amazon machine learning use this subset to learn hyperparameters and model parameters. And then the user will steer the hyperparameters learned by Amazon machine learning using our attack. And then the user will upload the entire training data set and specify the steered hyperparameter to Amazon machine learning. And then Amazon machine learning will relearn the model parameters over this entire training data set and the hyperparameter. And finally, the user will evaluate the testing data set by querying the learned machine learning model. Here, because we learn hyperparameters using a subset of the training data set, so it is efficient, and we learn model parameters using the entire training data set, so it is accurate. And here we compare the three methods on a bank data set using the Amazon machine learning. We use one half of the bank data set as training and the other half for testing. And we sample 15% and 3% of the training data set for M2 and M3. And Amazon will charge users according to the computational time. And then we calculate the training cost and the relative error. So here we see that compared with M1, M3 can save much training cost, but with a very small accuracy loss. And compared with M2, M3 has almost the same training cost, but the relative error is much more small. And then we show the difference. And here, we use the random as a defense. First, we run the learned model parameters before sharing the model parameters to the user. For instance, running a parameter at 0.8765 with one decimal is 0.9, and with two decimals is 0.88. And note that this running technique was also used by other work. And here is the defense results. And the x-axis is the number of decimals we keep. And in the left figure, it is the relative mean square error. And in the right figure, the y-axis is the relative estimation error. In the left figure, we see that the relative mean square error for the three methods are very slow. So it means that the random has a small impact on the model's performance. But in the right figure, we see that the ridge regression has a very large relative estimation error. So random is effective for a ridge regression. But for lasso, we see that the relative estimation error is still very small. So it means that the defense is not effective for lasso. So the first conclusion is that the random is not effective enough for certain machine learning algorithms. And also we see that the ridge regression and the kernel ridge regression have a larger relative error than the lasso when we keep the number of decimals to be 1. Ridge regression and kernel ridge regression use L2 regularization, and lasso use L1 regularization. So we can draw this conclusion. The L2 regularization is more secure than the L1 regularization. And then the conclusion. The first is machine learning algorithms are vulnerable to hyperparameter stealing attacks. And all attacks can help users save economical costs on machine learning as a service platforms without sacrificing the testing performance. And we need new defense for our hyperparameter stealing attack. That's all. Thank you.
We have time for a few questions. So let me ask the first question. I was wondering if you could sort of more precisely characterize what is the adversary model here. So what kind of adversary, what are the goals, what is the strength of the adversary for your attacks?
Beg your pardon?
The adversary model. Like, what is the adversary model here? Like, what is the goal of the adversary, and what are the strengths?
The goal is that.
Just to be clear, so in particular, like, what's the adversary for your attack compared to an adversary for a model extraction attack?
Mm-hmm. How can we perform the model extraction attack? I mean,
no. What is the adversary? Right? What is the adversary model? What is the goal and what is the power of the adversary?
The power.
Yeah, the capabilities and the knowledge
about my attack. Yeah. The capability is that your meaning about capability is about what? Is about
maybe we should take this offline. So let's thank the speaker.
Okay, sorry about that.